Special angles with the cast rule. Okay, special angles with the primary trig ratios. So, what you should have seen in the investigation is that there are two special right triangles that allow you to find the exact values of the primary trig ratios for the special angles 30, 45, and 90 degrees. So these are your three special angles, and what we're going to be solving for are exact values of the ratios. So for example, oftentimes you would have questions like sine of 40 degrees is equal to something, and usually you would type this into your calculator and the result would be a decimal answer. Well, this decimal answer is common for angles like 40 degrees. However, there are certain angles like a 30-degree angle that you can actually evaluate and find the exact value for. So if I look at the sine of 40 degrees, I get a decimal answer like 0.6427, etc., etc. And if I look at sine of 30 degrees, I can actually come up with an exact value. An exact value means no decimal answer. That's exactly the answer. So most of the time it ends up being in fraction form. So we're going to look at how to come up with the exact value of specific angles. And those specific angles that we're going to be looking at are special angles known as the 30-degree angle, the 45-degree angle, and the 60-degree angle. So there's two special triangles. One of the triangles are called the 45-45-90 triangle, in which there are two 45-degree angles and a 90-degree angle. And then there's the 30-60-90 triangle, where there's a 30-degree angle, a 60-degree angle, and a 90-degree angle. Each of these sides are strategically labeled. So this triangle, 45-45-90 triangle, since these two sides are the same, you know it's going to be an isosceles right triangle. And so these two side lengths will also be the same. So two angles and two sides are the same. The third side here, which is a hypotenuse, you can solve for using Pythagorean theorem. So if you do a squared plus b squared equals c squared and solve for the value of c, you end up getting the square root of 2. So that's how this triangle comes about. Okay, the second triangle is the 30-60-90 triangle, and this triangle is actually developed from an equilateral triangle that has side lengths 2. And so what ends up happening is, if you only look at half an equilateral triangle, you end up splitting the angle at the top here, which ends up being 30 degrees. This angle ends up being 60, and the right angle here ends up being 90. Now, the dimensions here, the side length of the hypotenuse, which is 2, and the shorter side here, which is 1, those are two sides that remain from the equilateral triangle that you normally start with to develop the 30-60-90 triangle, and then again you can use the Pythagorean theorem to solve for this side. Okay, so very similar idea. Both of these triangles are special triangles. You will need to know them in order to solve some of the problems that we're going to be looking at. Typically you would use these when you are given an angle and you're asked to find a ratio that corresponds to either sine, cosine, or tangent. One way to remember which sides correspond to which angles, since it is important that you make sure the correct angle corresponds to the correct side that it's labeled with. One way to remember that is by remembering that the smallest angle is always opposite the smallest side, and the largest angle is always opposite the largest side. So in this triangle, you can see clearly these two sides are the same. This side, if you approximate what root 2 is equal to, it's about 1.4. And notice that this is the largest angle, so that would also have to be the largest side. Similarly, in this triangle, this is the smallest angle, that's the smallest side. This is the largest angle, the 90-degree angle, and that's the largest side. The square root of 3 is about 1.7, and so that's the middle size angle across from the middle side as well. Okay, so what's the benefit of knowing the 45-45-90 triangle and the 30-60-90 triangles? Well, if you're asked to find the sine, cosine, or tangent of any one of these angles, whether it's a 45-degree angle or a 30 or 60-degree angle, you can find the exact value meaning you don't need a calculator to determine it. You can figure it out without the use of a calculator and without getting a decimal. Okay, and so for example, if I wanted to know the exact value of sine 45, I would look at my 45-45-90 triangle, look for a 45-degree angle, and look at the opposite and hypotenuse sides based on that triangle. And I know the opposite and hypotenuse for a 45-degree angle end up being 1 over root 2, which is exactly what I did here. Same idea for the rest of the ratios. Same idea here if I was looking at sine of 30 degrees or cosine of 30 degrees or tangent of 30 degrees. I would start by looking at the 30-degree angle and then looking at the ratio of the opposite, adjacent, and hypotenuse sides, depending on which ratio I'm referring to. So let's say I'm looking at the cosine of 30 degrees. I would find a 30-degree angle, find the adjacent side and the hypotenuse to get root 3 over 2 as the exact value of the cosine of 30 degrees. Same idea for a 60-degree angle. Let's say I'm looking at the tangent of 60 degrees. I'd find the 60-degree angle and find the ratio of the opposite and adjacent side. So root 3 over 1 gives me root 3. Okay, so that's what the good thing about having the special angles and the special triangles will be. Now we are going to also be referring to the cast rule when we're looking at the special angles. So remember the cast rule. Cast rule tells you which quadrants the trig ratio is positive. So cosines positive in quadrant 4, all of them in quadrant 1, sine only in the second quadrant, and tan only in the third quadrant. So we are going to be making reference to the cast rule. Okay, determining exact trig ratios. Here's the steps for determining exact trig ratios. Your first step, because you're going to be given the angle, if you're solving for the ratio, you have to be given the angle. If you're solving for the angle, you have to be given the ratio. So in this case, because we're solving for exact trig ratios, that means you're going to be given the angle. Okay, so what you will do using that angle is sketch a terminal arm diagram in the appropriate quadrant. So depending on what the value of your angle is, you should be able to determine which quadrant the terminal arm should fall in. Then we're going to determine the related acute angle, and the related acute angle we'll find similar to how we did yesterday or in lesson 2. We'll talk about that when we do some examples. And then the value of the related angle should be one of these special angles, either a 30-degree angle, a 60-degree angle, or a 45-degree angle. Now, using those special angles and the trig ratio that we are given originally, we're going to rewrite the given expression using the cast rule. So we'll be able to determine whether it'll be a positive or negative ratio. So the cast rule will help us remember if it's going to be positive or negative. And then we'll use a related acute angle as well. And you'll see that in a few minutes when we actually do an example. And then from there, it's just a matter of solving the new expression using the special triangles. So let's look at our first example. In example 1, it asks us to determine the exact values of the following. So we're solving for a ratio. We're given the cosine of 135 degrees. So our first step is to determine what the terminal arm diagram of this will look like. And because you're given the angle, you should know which quadrant this falls in. And because this angle is between 90 and 135, I know this will fall in quadrant 2. So I'm going to draw a terminal arm diagram with a focus on quadrant 2. And there's my terminal arm. So what this means is the angle of rotation from here to here is 135 degrees. Now my second step is to determine the related acute angle. So what I want to know is what the small angle in here will be. Now this is a little bit less than a half rotation. A half rotation would have been 180 degrees. This angle in here I can find by finding the difference between 180 and 135. So 180 degrees minus 135 degrees gives me 45 degrees. So this is going to be my 45 degree special angle. Now what I can do is I can rewrite the cosine of 135 using the cast rule and this related acute angle. Now the reason why I'm referring to the cast rule is so that I know whether or not the ratio will be positive or whether it'll be negative. And because this angle happens to fall in the second quadrant, sine is the only ratio that should be positive here, which means this ratio, once I actually find it, will end up being a negative answer. So I can rewrite cos of 135 as negative, since it'll be a negative result, the cosine of 45 degrees. Okay, so first the cast rule will help me determine what the sine of the ratio will be, and the related acute angle will help me make it easier to actually solve for the ratio. Now because now I have negative cos of 45 degrees, I can evaluate the cosine of 45 degrees by using my special triangle. So you'll notice that I actually wrote these out on the side. These are 3 pieces of information that I will always continue to make sure I have so that I can actually solve any of these special triangle problems. So the negative part is still there. The cosine of 45 degrees is equal to the adjacent over hypotenuse side. So I'm looking at the 45, 45, 90 triangle. The ratio of the adjacent and hypotenuse side is 1 over root 2. Okay, there is the exact value of the cosine of 135 degrees. So this is the exact value of the ratio. It's 1 over root 2. How can I check my work? Well, what I could do is determine what the cosine of 135 degrees is as a decimal. So it's about negative 0.707. And then do the same thing with the answer I got at the end. 1 divided by the square root of 2. And you'll notice I get 0.707 again. So I know that this is actually correct. The decimal answer and the exact answer give me the same thing. So when I calculated cos of 135, I got the same answer as negative 1 over root 2. Okay, and that's it. So this is how you would find the exact value of a ratio. So we're given an angle, we can find the exact value of the ratio. Let's look at a couple more examples. So in this example, it tells us to find the exact value of the ratio again, but you'll notice that we have a slight bit of a problem here. We have an angle that's more than 360 degrees. So what that tells me is this angle this terminal arm goes around the 4 quadrants, and then it continues to go through another part way through another cycle. Okay, so how can I get this angle within 0 and 360 degrees? Well, all I need to do is backtrack and go back 1 full rotation. And so what I could do is rewrite this angle as a smaller angle by subtracting a full rotation from it. And so if I subtract the full rotation from it, the terminal arm should end up back to where it was anyways. It's just less rotations instead of 1 full rotation and then some. So what I end up with is a sine of 240 degrees. Now I still haven't found the ratio. The ratio should be just a fraction at the end. It shouldn't have any trig expressions at the beginning. So now what I'm looking at is a sine of 240 degrees. All 3 of these mean the same thing. That's why I can show equivalency between them. And so if I draw my terminal arm diagram, 240 degrees is between 180 and 270. So what that tells me is that the angle will be in quadrant 3. So I'm going to draw a terminal arm diagram with the focus on the 3rd quadrant. And there we go. And so here's my terminal arm. And this angle of rotation from the positive x-axis to the terminal arm is equal to 240 degrees. Now I need to find my related acute angle. And remember, your related acute angle is always the angle that's created between the x-axis and the terminal arm. So this is the angle here that I'm looking at. Okay? And so then you'll notice that this angle here that I'm looking at is in the 3rd quadrant. And you'll also notice that the 240 degree rotation is more than half a rotation. And so the difference here between 240 and 180 will tell me what the angle is for the related acute angle. And that gives me 60 degrees. So my related acute angle is 60 degrees. Now I'm going to use a cast rule to help me figure out whether my ratio will be positive or negative. And because I'm looking at an angle in the 3rd quadrant, and my ratio here that I'm looking at is sine, sine is negative in quadrant 3, so that tells me that the ratio I'm going to get is going to be a negative answer. On top of that, I'm going to use a related acute angle, because using the related acute angle, I can actually use my 30, 60, 90 triangle to help me solve for the exact value of the sine ratio. So instead of writing it as sine of 240 degrees, I'm rewriting it using the cast rule to help me determine the sine, and then the related acute angle that should give you the same answer but just not the same sine. Okay, and you'll notice that if I actually do the sine of 240 degrees and if I do the sine of 60 degrees, the numerical part's the same, the sign might be different. So that's why it's important to put the negative sign here to indicate to make sure that the answer sign is the same. Now I can use the special triangles again. And so because I'm looking at a 60 degree angle, I'm going to look at the 30, 60, 90 triangle. And so I'm looking at the sine of 60 degrees. So I'm looking at opposite over hypotenuse to figure out the sine of 60 degrees. And that gives me root 3 over 2. So the negative is still there, and I get root 3 over 2.